All right, so let's start. Last lecture we were looking at the operation of a bipolar junction transistor. Let's continue our discussion from there. So what we had seen is that when we have an NPN bipolar transistor, we can look upon this bipolar transistor in the case where base emitter junction is forward biased and collector base junction is reverse biased. Under that situation, one can look upon the bipolar transistor. Of course, the forward bias diode is there between base and emitter. And we also saw that the current, the electrons which are injected from the emitter to the base, they move on to the collector. So even though the collector base junction is reverse bias, it gets a current. The collector gets a current here, IC. And the collector current, of course, is due to electrons injected from here. So the collector current depends on the base emitter voltage here, which we represent by this particular dependent source. So this current basically describes the current flowing in the collector terminal here, and it arises due to electrons which were injected from the emitter base junction here. So that's why it's a dependent current source. So this is a equivalent circuit that one can that depicts the operation of transistor in forward bias. We also saw that when we look at the transistor in forward bias, the ratio of the collector current and the base current is what we call as beta, the current gain of the transistor. And this circuit then, if I look at it, I can also represent then in an alternative form where I keep the diode as it is. Between base and emitter, I have a diode. And at the collector, instead of writing collector current as a function of base emitter voltage, which it is, but alternatively, we can also write collector current, we can see here, is beta times IB. So we can represent it as beta times IB, and this as a current dependent current source. So it depends on the current, and it flows across this terminal here. So it's a current dependent current source. So we can also represent our bipolar transistor in forward active mode in terms of a current dependent current source. In this case, we were representing it as a voltage dependent current source, and in this case as a current dependent current source here. Because note that IC arises due to IB here, and IB is linked with the diode here, and so we expect IB to be an exponential function of base emitter voltage, and therefore IC is also an exponential function of base emitter voltage here. So we write IC as some saturation current exponent VB by VT minus 1. That's how we write IC, and then IB, of course, in active mode is IC by beta. All right, so that's how the transistor can be looked upon in forward active mode. Okay, let's continue from there. So so this is the transistor in forward active mode, and these are the equations. And here I've drawn a particular way of biasing a transistor where the base, as you can see here, is common. Base is common, and the emitter base side we look upon as an input side of the transistor, and the collector and base we look upon as the output side of the transistor here, with base being the common terminal here. So we call it the common base configuration. The common base configuration because all the voltages are being referenced with respect to the base which is grounded here. Okay, so this is a common base configuration. And in common base configuration, then if I look at the input side here, the input side is the current that flows is the emitter current, and the emitter current, it should be anyway. So I can write it as base current and emitter current here. We'll come back to that in a moment here. Let's see. Yeah. So this is the operation. I'll come back to the common base configuration here. So this is the forward active mode that we have just studied. That base current is an exponential function of VBE. Collector current is an exponential function of VBE because both are related together, collector and base current. And collector current is independent of, more or less independent of, whatever voltage you apply here. As you change the reverse bias on the collector base junction to the first order approximation, it doesn't change much in the transistor here. So these are the characteristics that you get here. I'll come back to common base and common emitter in a moment here. All right. So any questions with respect to this mode of operation, which is called forward active mode? The forward active mode. Now, if you're wondering why am I calling it forward, well, you can see that what is happening is that I'm making one junction forward biased and the other junction reverse biased. Emitter based junction is forward biased and collector based junction is reverse biased. We call that configuration as forward active mode because and you can also think of a reverse configuration where base collector junction is forward biased and emitter base junction is reverse biased. Then you will call that as a reverse active. So that's where the forward to distinguish between the two situations. In one case, emitter based junction is forward biased, collector based junction is reverse biased. In the other case, collector based junction is forward biased and emitter based junction is reverse biased. So the two configurations are called, one is called forward, the other one is called reverse. Okay. And so these are the characteristics that we expect. The current, whether you take base current or the collector current, or you take the emitter current. Emitter current is the sum of base and collector current. Any of the currents, if you take, they depend exponentially on the base emitter voltage. Because after all, the current is arising from a forward biased diode. So as you increase the diode voltage, the current which is linked with this particular diode increases exponentially, and the current elsewhere also increases exponentially. So that's why this exponential behavior that you see here. And we saw transistor action. The current doesn't depend on the reverse bias that you apply on the other junction. Whether you apply more or less, the current is sort of independent of it. So that's the basic characteristic of a transistor in the active mode. But note that, as we have said, transistor is a three-terminal element. There are two voltages. If I take base as a common part here, there's a base emitter voltage, there's a base collector voltage here. There are two independent voltages, if you would like. This is one independent voltage. If I take base as a common terminal, this is one independent voltage, and this is another independent voltage. Now, based on these two independent voltages, you can have four possibilities. So, if we draw base emitter voltage along x-axis and base collector voltage around y-axis, so in the first quadrant, we see that both base emitter voltage is positive and base collector voltage is also positive. Both of them are positive. And if you look at positive means base is positive with respect to this thing here. So base emitter junction is forward biased. And if VBC is positive, it means base collector junction is also forward biased. So when both the junctions are forward biased, we call a transistor in that mode that it is operating in saturation mode. So forward and forward, both junctions are forward and forward. The other one that we just studied is the fourth quadrant. Base emitter junction is forward biased and base collector junction is reverse biased. So that's forward and reverse. So that's called forward active. And the opposite of it is where base emitter junction is reverse biased, base collector junction is forward biased. So we call that the reverse active. And the last one is where none of the junctions are forward biased. Base emitter is also reverse bias. Base collector is also reverse bias. Both the junctions are reverse bias. And reverse bias junctions, we know, carry very little current. So the transistor, overall transistor does not carry much current. So we call that also as a cutoff state. In that mode, the transistor is like very close to an open circuit. So four modes of operation. Each, the most important one for us is forward active. That's where all the amplifiers operate, forward active here. And saturation and cutoff and forward active, these are, all three of them are important when you are making digital circuits, digital inverters and gates and all that. All three of them may be important here. And reverse active, we seldom operate. Reverse active is, you can say, is a poor version of forward active. It's a poor version of forward active. You don't get any gain by operating a transistor. You don't get any advantages of operating a transistor in reverse active because forward active in almost all aspects is better than that. So if you're looking for a transistor characteristics which is specific to active mode, then you might as well operate in forward rather than reverse. Okay, so that's a sort of unused region. We don't normally operate here. But all three of them, of course, are important. And for this course, the most important one is forward active. But what happens is, that you may take a transistor, bias it in forward active, but because of circuit conditions, the transistor may slip into saturation if you're not careful. Okay, the transistor may, if you're not careful, may go into saturation mode. And we'll see pretty soon that once the transistor is in saturation mode, it cannot amplify. Amplification is only possible in forward active mode. In saturation, the transistor cannot amplify. So if you're biasing it in forward active, because of circuit variations, because of other means, if it does slip into saturation, the amplification will stop. So that's why saturation mode is important for us in the sense that we would like a transistor to stay away from saturation. So how to stay away from saturation, we need to understand. When does the transistor go into saturation and all of that. Okay, so it's important in a sort of negative sense that we don't want to go into this particular region as far as amplification is concerned. We would like to stay safely in this region, forward active. And of course, cut off, no current. So again, from a amplifier point of view, it's not a useful region again. Okay, so this is the most important region which we just studied. All these characteristics that we looked at were all forward active. Okay, so as we said, saturation is important also for us in the sense that we would like to avoid it. But let's look at what happens in a transistor when both the junctions are forward biased. Okay, both the junctions are forward biased. So let's see what happens here. So this is our transistor here. So base we have taken it as grounded here, and emitter is forward biased, negative voltage here, and collector right now, as you look at it, the collector is positive with respect to base. So right now it is reverse bias. So right now it is reverse bias. The transistor is not in saturation right now. Okay. Now what we are going to do is the following. We'll assume that the base emitter voltage is a constant. We'll not touch the base emitter junction. Okay. We'll not touch the base emitter junction, and we'll gradually start decreasing the collector voltage. So we'll start decreasing. We start from here. Note here, start decreasing. So when I'm here, collector is positive. Collector is positive, so my base collector junction is reverse bias. And we saw that once the junction is reverse bias, it doesn't do anything to the current. So the current is flat. And as I keep on reducing the collector bias, the current doesn't change. Later on in the course, we'll see there's a slight small variation, but first order approximation, the current doesn't change. So it remains flat because my collector is reverse bias. The moment I come here, the collector becomes zero biased. There's no bias on the collector. Still, current is the same. Now when I go on the left side here, the collector now voltage has become negative and the junction has become reverse bias. But we have just learned that even though you may make a junction forward biased, but if the forward bias is 0.1 or 0.2, it doesn't carry that much current. Okay, so there's no practical influence initially. It's as if it doesn't really matter because the forward bias on the collector base junction is 0.1 or 0.2 or 0.3 or 0.4. Nothing really happens. Once the forward bias on the junction becomes significant, then you start to see that the current is dropping. The current drops. The current begins to drop and begins to drop quite sharply and may go to zero also. And if I go further, it may become negative also. It may become negative also. All right. So that's the behavior. Now, why is this happening? As I said, our interest is not so much in the reasons why this is happening. That's the subject of a different course. But nevertheless, I'll spend a little bit of time to show you why the current is dropping. And eventually, it may go to zero. It may even become negative. Okay. So let's see why this is happening. So base collector junction is reverse bias here. Base collector junction is forward bias here. Forward active, saturation, all that. Okay. So why does current drop in saturation? Okay. All right. So for argument's sake, we'll take a specific case here. We'll take that once the junction is in forward active, we assume that we've applied a bias on the base emitter junction such that the base current is 0.01 milliampere. The electron current which is injected, which is same as collector current, is 1 milliamp. And the gain of the transistor, IC by IB, is beta. So this is when collector base junction is zero bias or reverse bias is the same. Okay. So we'll take that as an example. Now we are saying we are forward biasing this junction. Okay. We are forward biasing this junction, and we are not touching this particular junction, okay? Base emitter voltage we are keeping constant. So this junction keeps on injecting electrons of the same magnitude. There's a holes which are injected here, which is also of the same magnitude. The ratio of the two still remains 100. So this junction we are not touching. But this junction we are forward biased. Once we forward bias, you can see here, this junction will inject electrons. And holes will get injected here also. It's a forward bias junction. So now compare the two picture here. The two picture here is now with this forward biasing of this junction, you start getting electrons which are injected here and holes which are injected here. Okay, let's put some number. Let's say I've forward biased it. Let's say because you've forward biased it, let's say the electron current which is injected is 0.2 and the hole current which is injected is 0.05. So what is the net current in the collector now? Net electron current will become 1 milliampere minus 0.2, which is 0.8 milliamperes. What is the direction of the current? Remember, this is electron flow. So 0.8 milliamperes, in what direction is it flowing? In this here. In this direction here, okay? 0.8 milliamperes. There is an additional 0.05 milliamperes of whole current which is flowing here. So the net current that ends up flowing is 0.75 milliamperes. Alright? So once you can see that once I forward bias this particular junction here, there is a current, additional current that comes in. These additional currents are shown here. There's electrons which are injected now. It's also a forward bias junction. So electrons will get injected here. Holes will get injected here. And I've just put some number just to show you. Let's say this is 0.2, this is 0.05. And so the net current comes out to be 0.75 here. So you're saying why, why the current, which was initially 1 milliampere here, has fallen to 0.75 milliamperes. Now, if I forward bias the base collector junction even more, if I forward bias it even more, instead of 0.2, this may become 0.5. This may become 0.5. This will also increase, and this current may drop to maybe 0.4 milliamperes. If I forward bias it even more, this may also become even 1 milliampere. And when it becomes 1 milliampere, this will exactly cancel this, and plus this will be there. So what will be the direction of collector current? It's negative. It's no longer positive. It's no longer flowing in this direction here. So it all depends on how much collector bias I apply. And you can see here why the collector bias, with the increase in collector bias, forward bias in collector, the current begins to drop. So one of the characteristics of saturation then that you see here, note as an example, we got IC as 0.75 milliamperes here. The net base current, the current which flows into the base. See, purpose of base current is what? To supply the holes. So the net base current that flows in, part of it flows here and another part flows here. So the net base current that you see here is 0.05 plus 0.01, which is 0.06 milliamperes. IC by IB, the ratio of the collector and base current is only 12.5 and is less than beta. So this is the characteristics of saturation. One way of saying saturation is when both the junctions are forward biased. Base emitter junction is forward biased, base collector junction is forward biased. Another way of saying that the transistor is in saturation is when the ratio of IC by IB is no longer beta. It's actually less than beta. Okay, so IC by IB it depends on, it could be 50, it could be 12, it could be 1. So whenever IC by IB is less than beta, we say the transistor is effectively in this region. Okay, now as we can also see from this diagram that I can have a situation where IC by IB is 1. Right here, IC by IB is 1. But the transistor is not really in active mode. If you strictly want to talk about it, it is in saturation. But the effects of saturation have not come in. You can say in principle, yes, the junction is forward bias. But that forward bias is so small that the effects of saturation have not come into play. So effectively, saturation begins in terms of its consequences. Saturation begins in this region. When IC by IB becomes less than beta. Okay? So you can see the distinction between the two cases here. This is the forward active. Look at the current flow. Only one junction is forward bias. Electron hole here. IC by beta times IB is 1. Look at the saturation region here. Look at the additional currents here that come into play here. And IC by beta times IB is less than 1. So when we talk about saturation, effectively we'll consider that saturation has set in my bipolar transistor when this condition begins to hold. When IC by beta IB begins to be less than 1, we say, well, the effects of saturation are now manifest in my transistor. Otherwise, it's effectively like forward act. Okay? Yes.
Can you comment about the voltage VCB and VC?
All right. So you are asking at what point does this begin to occur? Okay. So the question is, okay. So what we are saying is it remains constant up to a while, and then it begins to drop. So when does it really begin to drop here? All right. So if you see, what we are saying is that this begins to drop when injection in this region also becomes significant as compared to this, right? When the electron current and the hole current start to become comparable with this, then only the current will begin to drop. So if we take, let's say if we take that this junction is forward biased by 0.7 as an example. Forward bias on this is 0.7. Now we saw that collector base junction is different from base emitter junction. If you recall the structure of the transistor, we said the collector base area is much larger. The junction area is much larger. The dopings are different. So it turns out that collector base junction, even for 0.5, let's say, if the forward bias is 0.5, the current becomes significant. In this case, let's say if you need 0.7 volts for a current of 1 milliampere to flow, for a collector base junction, you may need 0.5, 0.55, or maybe 0.6 for current to flow. So collector base junction is larger, it has lesser doping, and it has higher currents associated with it. So this, when you are saying when does this begin to occur, maybe it begins to occur when collector base voltage is, let's say, 0.5. It depends on how the transistor is constructed. But it's lower than the base emitter voltage. Okay, so this starts falling. We'll show you transistor characteristics later on, so you can see where it begins to fall. Okay. All right. So whatever I've been describing for you so far is forward active mode and saturation, and I've been talking mostly in the common base configuration, where base, as we said, is constant, and emitter base junction forward bias. This could be, if this is reverse bias, we are in forward active mode. If this is forward bias, then we are in saturation mode. And these are the characteristics that we get. All right. I can also operate my transistor in common emitter mode. Common emitter mode, note that emitter becomes my reference terminal. Emitter becomes my reference terminal, and the input side is base emitter, and the output side is collector emitter. So when you look at your transistor in this way, in the common emitter mode, the input side becomes the base emitter, the output side becomes the collector emitter. Now there are two sides, input side and output side. You would like to know, how does the transistor behave from the input side? Well, from the input side, what do I have between base and emitter? A diode. So input side, IB with base emitter voltage looks like a diode. All right, so that's fine. How does it look from the output side? Well, collector current is there from the output side. So I'm interested in collector current. And collector current is a function of two things. Collector current depends not only on base emitter voltage, but depends on collector emitter voltage also. So the dependence on base emitter voltage is again exponential, because collector current basically arises from the base current. In the forward active mode, you know collector current is beta times IB. So if IB varies exponentially, collector current also tends to vary exponentially here. So that's fine. The other one is collector current versus the collector emitter voltage. So that's collector current versus collector emitter voltage, shows a behavior of this kind here. Now, this we can recognize when collector current is independent of collector voltage, the transistor is in reverse bias. Okay, so we can, so this is input. These are two output characteristics. We can draw a line here. This is where the transistor is in forward active mode, and this is where the current starts to drop. The transistor is going into saturation mode. Okay, so that's the output characteristics in the common emitter mode. This is the, whenever, when the manufacturers or even in terms of use, whenever we are using a transistor, most of the time, we are using it in this particular configuration. With emitter grounded, forcing a current or a voltage at the base, taking output at the collector here. So this is the most widely used configuration, and that's why these characteristics are important. This is the input, base current versus base emitter voltage. Output, there are two parts of the output. Output current is dependent on both of them, VBE and VCE. IC with VBE is here, and IC with VCE, note that we plot it for constant values of base current. I mean, that's a part of convention. I can also plot things by saying that I can ask how does IC vary with VCE for a fixed value of base emitter voltage. One can do that also. For a fixed value of base emitter voltage, how does IC vary with collector emitter voltage here? But the convention, and there's a good reason for it, the convention is to plot IC versus VCE for fixed values of base current. For fixed values of base current, and you'll see very, for a bipolar transistor and even for a diode, you don't apply a fixed voltage to a diode. You don't want to do that. Let's say there's a diode which is there, and you want 1 milliampere of current to flow through the diode. Well, you're not going to apply 0.7 volt, let's say, to get 1 milliampere. Why would you not do that? Because you see, if you apply 0.7 volt and let's say you're expecting 1 milliampere. Now, if for some reason, whatever you're applying is not 0.7, is 0.72, what would happen? If there's a little bit of error, you wanted 1 milliamperes, you know that 0.7 will give you 1 milliamperes, but the way you are generating points, maybe you're generating 0.7 from a 5 volt supply. So 0.7, you don't get exactly 0.7, you get 0.72. How much will the current become? Current is exponentially function of voltage here. Instead of 1 milliamperes, you may end up getting 2 or 3 milliamperes. So you never, whenever you want a diode, you never try to achieve a certain current flowing through the diode by trying to apply a particular fixed voltage. You don't do that. You don't do that because that's highly unstable. Okay? So what you do is better that by using an external resistor and other things like that, you control how much current is flowing through the diode. Use the external circuit to control the current. Otherwise, the diode is very sensitive to the voltage here. You don't apply a fixed voltage. So similarly, when I'm looking at a transistor, you'll see that all the circuits that we'll encounter, we don't keep base emitter voltage actually fixed. We don't keep it fixed, assuming that the collector current then would get fixed at a certain value because it's so sensitive. So what is common is that maybe I'll keep the base current constant. I apply a constant base current and then look at what happens to the collector current. Okay, so that's a much more useful configuration. Then that's why you're seeing the collector versus collector emitter voltage is plotted for various values of base current here. IB1, IB2, IB3. Okay, so let's come back to this. This is an important characteristic here. Whenever you're handling a transistor, if you're making a transistor, if a transistor is given to you in the lab and you want to check, is my transistor working properly or not? Well, this is the signature. Try to measure, force a certain current into your base, say 10 microamperes, 20 microamperes or whatever, force a certain current into the base, plot IC versus VCE, see if you get this or not. That's the signature of a transistor. I mean, as a quick, if you want to see if the transistor is working properly or not, this is what you're looking for. A current which is constant and then current which begins to drop here. And this kind of a behavior here. Note IC versus VCE for different values of base current. So if we look at collector emitter voltage, let's look at this characteristics a little bit more detail here. If we look at collector emitter voltage, VCE, note that I can write VCE as VCB plus VBE. I can break VCE into two parts here. VCB means what? VC minus VB. And VBE means what? VB minus VE. So you can see that I can write it like this here. VCB, I can write it as minus VBC. Alright, just a simple this thing here. Now, I can take VBC on this side here and write VBC as, I've put VBE approximately as 0.7. Because we know that base emitter junction is, note that this is active mode and this is saturation. In both cases, base emitter junction is forward biased. Otherwise, note that base current will not flow. I have a constant base current will not flow unless the junction is forward biased, okay? So, base emitter junction, I take it as 0.7. And so, VBC becomes equal to 0.7 minus VCE. So, note that when VCE here, when I start looking at VCE here, when VCE becomes 0.7 here, at this point, what is the base collector voltage? At this point, note that base collector voltage approximately becomes equal to 0. When VCE, collector emitter voltage is 0.7. When collector emitter voltage is 0.7, VBC is approximately 0. And at this point, to the right of it, my collector base junction is reverse bias. And to the left of it, my collector base junction is forward biased. But note, as we said, the effect of forward bias does not set in until you make the collector base junction sufficiently forward biased. So initially, yes, it is forward bias here, but nothing really is happening because the forward bias is not enough. Once the forward bias starts becoming enough, the current begins to drop and eventually drops to here. All right. So when we are thinking of our transistor, right, we said we want our transistor to operate in forward active mode. We want it to be here. No, we want it to be here. Strictly speaking, forward active mode stops here. Right? Stops here. So you may say, well, if you don't want your transistor ever to go into saturation and you're very strict about it, you'll say, I don't want my VCE to go less than 0.7. That's what you would say. Never let VCE, collector emitter voltage in your transistor fall below 0.7. If you ensure that, you are always in forward active mode. But we know that, well, even though strictly speaking is not forward active, maybe I can go as far as this, right? As far as this, and still it's acting as if it is in forward mode. So if you really want to push the boundary, you may say, well, to ensure that my transistor is effectively acting as if it's in forward active mode, I can maybe push my VCE as close as maybe 0.2. I mean, these numbers vary. Somebody may say 0.25 or whatever. So you may say, I may push my collector emitter voltage as close as 0.2 and still ensure that my transistor is virtually, not strict according to definition, virtually is acting as if it's like in a forward active mode. Okay? So that's something to remember, that there is a voltage up to which you can push collector emitter voltage. And as you push it up to that value, the transistor is effectively in forward active mode. But once you go beyond that, then, it is falling very rapidly. Okay? And note that in this region here, again, saturation is characterized by IC by beta IB becomes less than 1. So in this region, IC by beta IB is 1. And when I go here, the collector current becomes small. Base current is still the same. So IC by IB is less than beta IB. So this is the characteristics of saturation. Now, interestingly, the behavior, if you're thinking that why is this current dropping here? Okay. I explained to you why the current is dropping, but the reasons are slightly different here. Why is the current dropping in this case here? Let me explain. Okay. Let me remind you what we had discussed earlier. Look at this picture. We had reminded you earlier we were looking at common base. And we said this is active mode. And when I forward bias my base collector junction, this is saturation. And we have seen that current drops from 1 milliampere to 0.75 milliamperes. Now, what is the difference between common emitter? In common emitter, we said we are not keeping base emitter voltage constant. What are we keeping? Base current constant. That's a very, very important distinction. Whether you keep base emitter voltage constant or whether you keep current constant. So here, note that I'm keeping base emitter voltage constant. When I go from here to here, I kept base emitter voltage constant. Why? Note that this remained 1 milliampere, this remained 1 milliampere, this remained 10 microamperes. I didn't touch the base emitter junction. I only increase the collector base junction. Now the situation is different here. Look at the common emitter mode here. What am I doing in the common emitter mode? The base current is constant. I'm not keeping base emitter voltage constant here. The base current is constant. So now note that when base current is constant, let's say 10 microamperes, collector base junction is reverse bias. This junction is reverse bias. So what happens is this 10 microampere current, that base is there. This is holes, they get injected here. And then there is an electron which is injected here. I get this kind of a behavior. And the net collector current is 1 milliampere. The entire 10 microamperes current that is in the terminals of the base, that all goes here. Because this is the only junction which is forward bias. Okay. Now, when I forward bias this junction also, when I forward bias this particular junction also, then this 10 microampere current has to go not only with this, but this is also forward bias. So both junctions are demanding current. So 10 microampere current that you see here, it, as an example, it distributes, only 8 goes here and 2 goes here. Earlier, the entire 10 goes here. So now 8 goes here. Now what does it mean? If you think about it, earlier 10 was going here and now 8 is going here. What does it mean? That base emitter junction is a little bit less forward biased now? Because earlier 10 microamperes of current were being injected, holes were injected. Now only 8 is being injected here. So the base emitter junction has become a little bit less forward biased. Little bit less forward bias means it is, earlier it was injecting 1 milliampere. Now it injects only 0.8 milliampere. So this 0.8 milliamperes happens here. And now this junction is also forward biased. So you get 2 microamperes here, you get 0.08 here. Effective current, when you calculate, you get 0.7. So now if you compare the two, why has the current fallen? What do you think is the reason current has fallen? What would you, as an explanation, why would you say, earlier I had 1 milliampere current. Now the current has fallen to 0.7 milliamperes. Why? What is the reason it has fallen? Yes, collector base junction is forward biased, but what has happened as a result of forward biasing of the collector base junction? The current, 10 microamperes, which was earlier going entirely here, now part of 10 milliamperes goes here. The base current is being diverted earlier from base emitter junction to base collector junction. And as this becomes 8, this also becomes smaller. So what is happening is that the current which is injected from the emitter, which was 1 milliampere, has become 0.8. The current itself has fallen. The injection from the emitter to the base itself has fallen to 0.8. And that's the dominant reason why it has gone to 0.7. Note earlier this was 1 milliampere here, it stayed 1 milliampere here because we didn't touch the base emitter junction. And the reason why it has fallen to 0.75, this 1 milliampere gets cancelled by this injection from here. But in this case, this 1 milliampere itself has become 0.8. The cancellation is there, but it's much smaller. It's only 0.08. It's only 2. So it's quite different in terms of why the current is falling. The current is falling here because the base current that you see here, earlier it was flowing in base emitter junction, is getting increasingly diverted here. Now, if you apply forward bias even more on the collector base junction, instead of 2 microamperes, what may happen is 4 may flow here. And if 4 flows here, then what will flow here is only 6. And therefore, this current will drop even further. Okay? So it's interesting that how things, what is really happening inside the transistor, depending on whether you keep the base emitter voltage constant or depending on whether you keep the base current constant. Okay? Very often, in fact, in most of the textbooks that you'll find, this is an error that you'll find in almost everywhere where people think that the current is falling here in common emitter mode because of a similar process. The current is falling in common emitter mode because of a different process here. The base emitter junction, this is where a issue comes in. Issue in the sense that, we keep on saying when there's a diode, the forward bias, when the diode is forward biased, the voltage across is 0.7. Right? You've all seen now, 0.7 is an approximation. And we keep on thinking that is 0.7, and therefore once it is forward bias, it remains forward bias here. But what is happening is, even though let's say this voltage was 0.7, the voltage slightly decreases here across the base emitter junction. Slightly decreases here. Why? Because there's less of current available here. Less current means less voltage here. And so this redistribution of base current is responsible for the falling of current. Anyway, the important point, at least from amplification point of view, is to be aware of a transistor which looks in this particular manner here, where beyond 0.2 or so, we are in the effects of saturation setting. Okay. All right. So how do I look upon a bipolar transistor in saturation mode? In terms of circuit now, once I go to a circuit, so if you look at it, between base and emitter, I still have a diode, no problem. Between collector and emitter, note between collector and emitter, what we are saying is, in this region, this is the saturation region here. This region is pretty sharp. Current is falling quite rapidly here. And so we say in the saturation region, the voltage, if it's a very sharp region here, we approximate it by a vertical line. We say the voltage across this particular region is almost fixed. And we say a typical value that we take, just like 0.7, we take for diode voltage, a typical value for saturation voltage we take as 0.2. So if you want to look upon a transistor in saturation, then between base and emitter is a diode. Between collector and emitter, we say the voltage is not changing much. The voltage is not changing much. So we approximate it by a constant voltage, which is VC sat. Saturation voltage. We take it as 0.2. And note that IC is not equal to beta IB. Okay. Well, if you want even a simpler model, then you take this diode and you approximate it by a 0.7 volt. So any circuit in saturation, a very quick analysis you can do by assuming that between base and emitter there's a 0.7 volt here, and between collector and emitter there's a 0.2 volt battery. Right? And check it out. Now you may make the assumption that my transistor is in saturation region. Do your analysis, find out your IC, find out your IB. How do you know whether this assumption is true? Check for IC divided by beta IB. If IC divided by beta IB comes out to be less than 1, then you've applied the right model. The model is fine. The transistor is indeed acting as if it's in saturation region here. Okay. If IC by beta IB doesn't come out to be less than 1, then your transistor is not in saturation. It's probably in forward active. Okay. All right. So that's a sort of summary of common emitter model of a transistor in common emitter mode. So in forward active, again 0.7, but between collector and emitter, we have beta times IB. And in saturation, we have 0.2. Okay, so these two situations. Now, so far we've talked about bipolar transistor in forward active and saturation. There are two other modes which are remaining: reverse active and cutoff. So let me just give you, there are places where the transistor may be in cutoff mode, may happen to be in reverse active mode, and how do you go about analyzing such circuits? So what we need is not really, one way of doing it is I have a specific model for forward active, I have a model for saturation, I have a model for cutoff, I have a model for reverse active. I can have 4 models. And looking at the circuit, I decide which model to apply. Mathematically or conceptually, you may say, well, why not have one general model? One general model and just apply it, and my analysis, or once I do everything, it will be taken care of, whether it's active, forward, reverse, or saturation. So you can feel that maybe what we need is a generalized transistor model. Now, where generalized transistor models are important, not so much for us in the sense that while doing the analysis, because generalized transistor model, as you would see, if it's a model applicable everywhere in all the modes, the model will become complex. The model will become complex, your analysis will become complex, and we don't want to do that. Actually, we are quite happy with a model which works in forward active, a more simplified model in saturation, simplified model in various places. We are quite happy with that because we want to do quick analysis. But imagine that you're writing a computer program, a simulator. Now, in a simulator, how do you decide, should I apply a forward active model or a saturation model or a reverse active model or what? So in a simulator, I'll go ahead and put this generalized transistor model, which is applicable everywhere. Okay, so these models and higher versions of it are nice for when you're doing simulation. Okay, so how do we? I'm not doing a rigorous derivation of a generalized transistor model. What I'm pointing out is a sort of a discussion which may make it easier for you to appreciate. Yes, that's what a general model may look like. So forward active, everybody agrees. This is what we have. Forward active. Can I write the model in these terms also? Forward active. In this base collector emitter, in this case, we put base here, emitter here, collector here. And can I write it in this form? Look at the diode direction. Diode direction is from base to emitter. It's still from base to emitter. There is a current. We are saying IC is related to IB by beta times IB. Well, we know that all these currents are anyway related together. IC, IB, IE. IE is the sum of IC and IB. So I can also write IC is, take this as an input, call this as the emitter current. IC is alpha F times IE. So I can write IC in terms of beta IB, or I can write IC in terms of alpha IE. And we can derive very quickly what is alpha. So IC is beta times IB, IE is sum of IC plus IB here. And so IC can be written as alpha F, beta F by 1 plus beta F. So, okay. Now, this, as its name indicates, beta will be called as the common emitter gain, because emitter is the common terminal, so you call it common emitter. F stands for forward active, so it's a common emitter gain. This one, because base is common here, you're linking IC with IE here, you call is the common base gain, alpha F. Anyway, so this is just the same circuit redrawn here, except that you've taken emitter current here and you've used alpha. All right, let's look at this one here. Any change? I've just redrawn the circuit. I've just taken this one here, turned it 90 degrees, taken the base terminal here. Everything is fine. Okay. Some change in terminology, as you can see here. We say the current flowing through this, we call it IF through this diode. Then this is alpha F IF here. If you can see, alpha F IE, alpha F IF here. Fine. Everything is as it is, except with a new terminology, new current, which we are just calling IF. This is forward active. Reverse active, can you imagine what it will be? This forward active. Can you see reverse active? Reverse active mode. When this junction is forward bias, this is reverse bias. Exactly the opposite. This one here, diode, we call it IR, reverse current. We call this alpha IR. Okay? Look at these two now. Forward active and reverse active. This is forward active. When this junction is forward bias, this junction is reverse bias. This is what you have. Reverse active. This junction is forward bias. There is a diode which is forward bias now. And whatever is the current flowing in this diode, a part of it flows here also, alpha R times IR here. Right? Now, a model where both the junctions are forward bias or reverse bias or whatever, what would happen? This is one case, this is another case. As I said, I'm not doing a derivation. I'm just making it easier for you to think, yes, that this is likely to be the answer. A general model. A general model of a transistor. Now, let's see if I am reverse active. Reverse active means this diode is reverse biased, IR equal to 0. alpha or IR equal to 0, it goes back to this mode here. Okay, reverse active, IF equal to 0, alpha if IF equal to 0, it goes into this mode. So a general model of a transistor is what we call, it goes by the name Eber-Small model, which is given. You can use it in saturation, you can use it in linear, forward active, reverse active, any of the modes, you can use this particular model. Before you leave, one last point that will come back to that. It's an important point to note that when you look at a bipolar transistor, you see two diodes, one diode here and one diode here. A bipolar transistor is not simply two diodes connected back to back. Look at the difference between this picture and look at this picture. This is what a bipolar transistor is. It's not just two diodes. What is the most important thing in a bipolar transistor? Two diodes that you see here is fine. Whatever is the current flowing here, a part of it flows here also. This linking of the two junctions. The linking of the two junctions. Whatever is IR here, something flows here. The linking of the two junctions. That's the bipolar action. That's where all the transistor action is. It's not simply two diodes that is over. Okay, so let's stop.